Good afternoon, everyone. We are from the Department of Statistics of the CUHK. I am pleased to be here today to talk about one of the most important constants in all mathematics, the number e. This is an introduction to the number e. Let us begin. So, where does the constant e come from? As we all know, Euler's number, denoted by e, is also known as Napier's number. In this chapter, we will sketch a few natural contexts in which the constant e emerges. Well, let's start with an example of continuous compound interest. Assume a bank account with an annual interest rate of 100%. At the beginning of the year, the account holds exactly $1, and the interest is credited to the account n times a year at regular intervals. We calculate the bank account's final balance Fn after 1 year for n equals 1, 2, 3. We notice the pattern that arises. In general, we have Fn equals open parenthesis 1 plus 1 over n close parenthesis to the power of n. As we reduce the crediting period towards 0, we may speak of continuous compounding of interest, or equivalently let n approach infinity. We may convince ourselves that the final amount might actually approach a limit. Motivated by this example, we define e as the limit of open parenthesis 1 plus 1 over n closed parenthesis to the power of n as n approaches infinity. The number e is irrational and its approximation to 3 decimal places is 2.718 as indicated already in the example. The symbol e refers to Swiss mathematician Euler, who was the first to see its significance in mathematics, although the Scottish mathematician John Napier had introduced e earlier as a natural basis for logarithms. Next, let's consider an example of continuous compound interest in general. Assume a bank account with an annual interest rate p%. Let alpha equals 1 over p be the corresponding growth factor. At the beginning of the year, the account holds exactly $1, and the interest is credited to the account n times a year at regular intervals. We calculate the final balance Fn after 1 year for n equals 1, 2, 3. In general, we have Fn equals open parenthesis 1 plus 1 over n times alpha close parenthesis to the power of n. When n approaches infinity, the interest is compounded continuously and the final amount will be F infinity equals e to the power of alpha. For example, if p equals 5 and alpha equals 0.05, we have F infinity equals e to the power of alpha equals e to the power of 0.05 approximately equal to 1.05127, while F underscore 1 equals 1.05 and F underscore 2 equals 1.050625. In short, we discussed the concept of limits of sequences and saw how they are used to define a number, m+. Now, let's move on to example 3, which involves Bernoulli trials. Jacob Bernoulli, a Swiss mathematician and Euler's predecessor, considered the following problem. In a bowl, there are n balls, all except one of which are white, and the exceptional one being black. A gambler picks one ball at random, checks its color and puts it back into the bowl. This is repeated n times. The question is, what is the probability Pn that the gambler never gets the black ball? And what limit does this probability approach when n increases towards infinity? To solve this problem, we use the product rule and the fact that successive draws are independent of each other. At each draw, the probability of not getting the black ball is given by 1 minus 1 over n. Therefore, The probability of getting the same result at each of the integers is given by the expression 1 minus 1 over n raised to the power of n. For example, when n equals 100, we have p sub 100 equals 1 minus 1 over 100 raised to the power of 100, which is approximately 0.366. It can be proved that as n approaches infinity, p sub n approaches the value of 1 over e, which is approximately 0.367879444. Moving on to the next section, we see that besides the limits of sequences considered above, the number e can also be expressed as infinite sums. The most useful of these is the infinite series representation, the sum of 1 plus the fraction 1 over 1 factorial plus the fraction 1 over 2 factorial plus the fraction 1 over 3 factorial plus the fraction 1 over 4 factorial and so on, equals the number e. This follows from the more general result that the exponential function e to the power of x can be represented as a power series, the sum of 1 plus the fraction x over 1 factorial plus the fraction x squared over 2 factorial plus the fraction x cubed over 3 factorial plus the fraction x to the 4th power over 4 factorial and so on, equals the exponential function e to the power of x. It can be proved that this equation holds true for all real values of x. Note that by setting x equal to -1, we obtain the expression, the fraction 1 over e equals the sum of 1 minus the fraction 1 over 1 factorial plus the fraction 1 over 2 factorial minus the fraction 1 over 3 factorial plus the fraction 1 over 4 factorial and so on. Here, I'd like to mention that the infinite series representation for e can be justified directly by applying the binomial theorem to its definition. In the case of the more general equation for e to the power of x, we again apply the binomial theorem to the definition and obtain a similar power series representation. So far, we talked about the transcendental nature of the Euler-Napier number, e. In this section, we will discuss another interesting aspect of this number, its irrationality. As the theorem states, e is irrational. Let me explain why. Assume, to the contrary, that e is rational, that is, e equals p over q for some integers p and q where q is not equal to 0. Using equation 4, we can see that e is equal to the sum of 1 over k factorial from k equals 0 to infinity. Then, we can break the sum into two parts, the first being the sum from k equals 0 to q of 1 over k factorial, and the second being the sum from k equals q plus 1 to infinity of 1 over k factorial. Next, let's deal with some mathematical manipulation. Transposing terms, we get the equation p over q minus the sum from k equals 0 to q of 1 over k factorial equals the sum from k equals q plus 1 to infinity of 1 over k factorial. Multiplying both sides by q factorial, we get p times q minus 1 factorial minus the sum from k equals 0 to q of q factorial over k factorial equals the sum from k equals q plus 1 to infinity of q factorial over k factorial. We can simplify this by noticing that the sum from k equals q plus 1 to infinity of q factorial over k factorial is less than the sum from k equals 1 to infinity of 1 over q to the k, which is less than 1 over q and less than 1. We also notice that the sum from k equals q plus 1 to infinity of q factorial over k factorial is positive, and it is also less than 1. Therefore, the left-hand side of the equation is an integer, while the right-hand side is between 0 and 1, making the equation impossible. But this equation followed from our assumption that e is rational. Hence, the assumption must be false. Therefore, e is irrational. It is interesting to note that Charles Hermite, a French mathematician, proved in 1873 that not only is E irrational, but it is also transcendental. In fact, almost all real numbers are transcendental, as Georg Cantor, the creator of modern set theory, proved in 1874. Now, let's move on to the representation of E as a simple continued fraction. Simple continued fractions are of the form 2 plus 1 over a finite continued fraction. All positive rational numbers can be expressed in this form. Irrational numbers, on the other hand, can be expressed as non-terminating infinite continued fractions. For example, the square root of 2 is equal to 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, and so on. It can be shown that the Euler number E also has a quite regular representation as a continued fraction. The continued fraction representation of E is 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 1 plus 1 over 4 plus 1 over 1, and so on. Thank you for listening, and I hope you have enjoyed this presentation on the introduction of E and its underlying concepts.